Practice problem number 2. A 567 kilogram car is traveling down a hilly road. If the car is at the top of a 15.1 meter hill and is moving with a speed of 19.1 meters per second, what is the potential energy relative to the bottom of the hill? What is the kinetic energy? What is the total energy? In this problem, we're going to start Donkey Kong Eats Stray Cat. So Donkey Kong, we're going to draw a picture. We're going to do our knowns and unknowns. We usually do those together. This car, we know what the mass is. It's given, 567 kilograms. We know its velocity at the beginning of the trip is 19.1 meters per second. And we know its displacement is 15.1 meters. That's going to be down to the bottom of the hill. The problem asks us our unknowns. Our unknowns are potential energy, kinetic energy, and total energy. All right, Donkey Kong Eats equations. Okay, we're looking for potential energy. Equation 8.2 tells us that the potential energy is equal to the mass times gravity times the height. In this case, the delta x and the height are the same, right? That's our vertical displacement. Donkey Kong Eats Stray. Stray would be to solve, so we're going to solve this equation for potential energy. It's a simple plug and play. You put in your mass, you put in your gravitational constant, and you put in your height. Now, a note about units. In this case, we've got kilograms, we've got meters per second squared, and we've got meters, so life is good, and we are smiling. But keep an eye on those. All right, the rest of that is simply punching buttons in your calculator. I'm confident you can do that. You end up with 83,904.66 kilogram meters squared per second squared. I went ahead and wrote all that out, but you all know that that is the same as a joule. Now, if you take a look for our significant figures, this thing here, 9.8 meters per second squared, is going to limit us to 2. So the only way to do that is going to be to write this in scientific notation. I guess you could write it with zeros, but you'd have to, well, I think scientific notation is going to be the only way we can do that. So 2 sig figs, 8.4, so 839 becomes 8.4 times 10 to the fourth what? Joules. Okay, so we've got our potential energy. Now our kinetic energy, and you'll see that I use 3' for that, right? We're following the Donkey Kong Eats Stray Cats thing again, but this time we're looking for something new. In this case, our equation is kinetic energy is equal to 1/2 the mass times the velocity squared. It's equation 8.3. Again, plug and play. We know the mass, it's in kilograms, that's good. We know the velocity is 19.1 meters per second, and we will be sure to square that. You end up there with 103,423.6 kilogram meters squared per second squared. Good, we know that's a joule. And again, we're limited to, well, in this case, 3 significant figures because we've got the 19.1 here, 567 here. That could actually have an infinite number. We don't know, but we do know that this one is just 3. So when I limit myself to 3 sig figs, I get 1.03 times 10 to the 5th, right? We moved it 1, 2, 3, 4, 5 places. That's how we got this 10 to the 5th. And we are in joules. Hallelujah. 2 out of 3. The third one's pretty easy. This can be 3 double prime. All right, so my equation is equation 8.4, which gives us the total energy. It's simply, because we're only dealing with mechanical energy, it's the potential energy plus the kinetic energy. Well, guess what? We already know what the potential energy is. We already know what the kinetic energy is. All I've got to do is add those together. Now, I ran out of space, so I did them vertically, okay? But I think you can handle that, and you end up with our total energy is now equal to 1.87 times 10 to the 5th joules. That's how you would do a problem like that.